I hope I'm audible. Ramuju Pavanteja, can you hear me? Okay, great. Great, thank you. Good evening. So, welcome to your fourth discussion session in Mechanical Behaviour of Materials. I am Pragyandipta Mishra, research scholar from Department of Applied Mechanics and Biomedical Engineering at IIT Madras. And today we'll be discussing about flow stress, yield criteria, followed up with effective stress and strain, and then problems on the same. So, with that out of the way, let's begin today's session. Yeah. So, let's start with flow stress. Now, whenever we apply any type of uh, loading on the material, we can draw stress strain in a particular way, right? For instance, if we are applying load, let's say we are applying load on the material, the stress versus strain graph would vary something like this, right? Now, for instance, if we stress the material up to some point, okay, say, let's say this is your yield limit. Let's say we stress the material up to the yield limit and then we remove the stress. What will happen to the material? The material just returns back to its original uh, non-stress state, right? But which path will the material take? Will the material return back the same path it has taken, or will there be a difference in the path? Now, previously we had seen that till elastic limit, we will see that there is no deformation induced in the material, no permanent deformation induced in the material. However, once the limit has been reached, once the elastic limit has been reached, and we go to yield limit and all, then when we unload the material, when we remove the load, the stress it will follow a stress strain path in which it will be parallel to the elastic limit, but not exactly following the same path. So there will be some amount of permanent deformation which is set here. So here this is the permanent deformation that can be seen in the material. Okay. Now, what happens if we re-stress the material? If we stress the material once again, now this will follow the same path that it has taken earlier. This will go back the same path, this path only, the red line. It will hit this point and it will keep going further. Now the yield limit yield limit becomes this point. Okay, the new yield limit. Now again, if we remove the load, it will come back here. Because again, that permanent deformation that we saw, that we have seen earlier, now it has increased to a new permanent deformation, and then the same process will keep going on. Now again, if we stress it, it will take this path once again, and then go till here, where this point will now become the new yield limit, and then again it will come back. Now, why is this happening? Essentially, what happens is the material. If we look at it from a mechanical point of view, and not considering the material science behind it, if we looking at it just from mechanical point of view, as we keep loading the material beyond the elastic limit, the strength of the material keeps increasing. Okay, so this is something that you can note down. Just a second. Yeah. Strength of the material keeps increasing with the deformation. Now, why this happens has, like, there is a reason essentially why this happens. So if you look at it from material science perspective, you will see that there are any specific specimen or material that we look at, has dislocations within it. Okay, we'll study about dislocation in the upcoming classes, what dislocations are and how they define the material behavior. But for now, you can just understand that dislocations essentially help in influencing the material behavior. And if you are moving or blocking dislocation in a particular way, then the strength of the material can go up or down depending on how you are controlling the motion of dislocation. Okay, for now you can just remember that the strength of the material keeps increasing as we keep deforming it within the plastic, like in the plastic region. Okay, so if you go beyond the elastic region and in the plastic region, if you keep deforming, then strength will keep on increasing. Okay, so then what is this flow stress that we are talking about? Essentially, this flow stress is the instantaneous value of stress to keep deforming the material. Now, very important. This flow stress is essentially a region, like you can say it's a region of stress that we keep looking at a particular instant of time. So at every instant of time, what is the value of stress that will allow us to ensure that the material keeps getting deformed? Essentially, what you are doing is you are plastically loading the material, and what is the minimum value of that plastic loading gives you this value of flow stress. So where does plastic stress usually set in? At what point? So this is why we are defining something known as yield point, right? Because that's where the plastic deformation kind of starts setting in, because the material starts yielding, right? So the locus of your yield point gives locus of a yield point gives the flow stress. Essentially, where the yield point is located at that particular instant of time will give you the value of flow stress. Okay. So so if the material keeps getting strengthened over time as we apply deformation, like you can see in this example that we are looking, like we have seen here. So your locus of yield stress or flow stress will keep moving up. Okay, so you will have the flow stress keep like as and when the flow stress keep moving up, your yield strength also keeps moving forward, and flow stress also keeps moving forward, right? So this is the essential concept of flow stress. Now uh, there is a way in order to like define or model this flow stress. Okay, so if we need to model flow stress, we can use something known as power law. Okay, so this is a very straightforward basic equation. You can just remember it as your stress, true value of stress is equal to K times epsilon T to the power N. Okay, so true stress and epsilon and true strain. Okay, so true stress and true strain are related by this expression, which is the power law. Now here your K is known as strength coefficient. While your N is known as strain hardening exponent. So as the name suggests, just a second, I think somebody is trying to join. Okay. Yeah, so as the name suggests, the strength coefficient will control how quickly the material will get strengthened or how slowly the material will get strengthened, while strain hardening exponent will control the rate of strain hardening. Okay. So now let's try to understand what exactly this rate of strain hardening is. So, rate of strain hardening is essentially the rate of change of true stress as a function of true strain in a material, which is undergoing any sort of plastic deformation. Okay, so let me write it down so that you can. Change of true stress. Sorry, rate of change of true stress as a function of true strain. In a material undergoing plastic deformation. Okay, that is mathematically, if I want to write it, what does this mean? Rate of change of true stress as a function of true strain. D sigma by d epsilon, right? So that is your rate of strain hardening. So if I calculate this, if I differentiate sigma with respect to epsilon, okay, what will I get? So I will get k times epsilon to the power n will become epsilon to the power n minus 1, right, times n. Okay, but k into epsilon to the power n is equal to sigma. So k into epsilon to the power n minus 1 will be equal to sigma by epsilon. So I can rewrite this as n times epsilon sigma by epsilon. So this what would this mean? What does this mean? N times sigma by epsilon. If your rate of strain hardening is proportional to n times sigma by epsilon. Now n is of course something that is controlled by material, right? What is the material behavior? But sigma is something that we can control, right? So in order to ensure that the material deforms faster, then you need to apply more amount of stress. If I write it down, this means that if the rate of deformation needs to be increased, sigma has to be increased. So essentially, your rate of deformation becomes proportional to stress value. So more stress would imply higher rate of deformation. Another important thing that you have to keep in mind, because this entire concept of strain hardening and strength essentially for any material system is dependent on what kind of material we are looking at. So This rate of strain hardening is very sensitive to the microstructure. Okay. So if you change the microstructure in some way, either by some processing technique or by addition of other material systems or doing something to the material in some way, your rate of strain hardening will also be influenced to a large extent. Okay. So I think there was one example that was shown in the NPTEL lecture, where sir had shown how if you take the same material, you anneal it or you age it, underage it, peak age it or overage it, you will see that your curve will change accordingly, right? Your stress strain curve will change accordingly. So depending on how the stress strain curve lies, you can see where your uh, rate of strain hardening will be changing accordingly. So essentially, for the same material system, depending on how you are processing it, influences your rate of strain hardening. Yes, because the microstructure in effect will change depending on what kind of processing technique is being used. Okay, so this is something that you have to keep in mind. Okay, so the next thing that we need to talk about is probably some examples of power law. So let's say I want to talk about how we can represent this power law for different material systems. So there are a few specific cases that we have to look at. So let me draw the stress strain. So if your stress is constant, sigma is equal to some value y, let's say, then this is a perfectly plastic material. Okay, this is perfectly plastic. I'll write it in. Probably should write it in a different ink. Yeah. Okay. Now another case could be your stress and strain are related linearly. Okay, so you might have something like this. So in which case your sigma is equal to some, let's say, some p times a plus a times, sorry, p plus a times lambda. Now a is some coefficient, the linear relation between sigma and epsilon is given by that a. Okay, and then p is basically some point, some stress sigma naught. Okay, or p here, I'll just write p directly. P from where the stress strain curve starts. Okay, so this is essentially a linear relationship. Now if the curve starts at 0, then that p value becomes 0 essentially. Okay. Now another way it could, the stress strain curve could look like would be something like this. Now this is the general case what we have been discussing till now. And something that most materials show. So it's same as what we have discussed till now. Sigma is equal to k times epsilon to the power n. Now the same thing could also another thing that could happen is that your material may not start at, let's say, at should if it may not start at 0. Just a second, I think someone is trying to join. So yeah, so like I was saying, it may be true that there might be some initial strain that might be existing within pre-existing strain which might be existing within the material. So your curve could start at some negative value epsilon naught or some positive value as well. It could start anywhere in the strain region. So your sigma value will be equal to this epsilon plus epsilon naught times n, right? And if epsilon naught is in the positive region, it will be epsilon minus epsilon naught. Okay. Now, why this case could exist? Can anybody think why could we have this case? Or let me show you another case that could exist. Let's let's talk about both the cases together. So what if there is a case something like this? The curve starts at some sigma naught. Okay, and your this value becomes sigma equals to sigma naught times 1 minus exponential minus E epsilon. Okay. Now, why could these cases exist? Why could your curve start here or here in the last two cases that we discussed? Why wouldn't it start at 0? Does anyone have any idea of any practical example why this could be the case?
What, sir? What, sir?
So essentially, in the last two graphs that I've drawn, let me just mark it so that you know this one and this one, the last two, the ones I ticked in red. Why could this case exist? Why wouldn't stress strain start at 0? Like at 0 strain, 0 stress. Why are we not starting there? Why are we having some negative value at 0 stress or something? Negative value of strain or some positive value of stress at some like why are we starting at some random values instead of starting at 0? And this actually exists in real life.
Sir, in case of polymers?
Polymers, yes, could be one thing. But if you can think about any structural application, because polymer is not a structural material, it's a functional material. But if you are thinking about structural application, why could this case exist?
Sir, like let's say if we have loaded in one direction and then we are loading it in opposite direction. So
Okay, that could be okay. So agreed. Like our friend here said, we could have loading like being changed cyclically. So because if you have loaded in one direction, then you're loading in the other direction, then you might start at some other value. Agreed, that could be one thing. But there is a very practical example as to why this is the case. So I think I'll explain it to you. So essentially what happens is, whenever you're laying down roofs in houses or you're laying down bridges, right? What kind of load will you be worried about? Whether it's in roof or whether it's in bridge. Like for instance, you're making a very high-rise building. You have one roof above the other, right? One floor above the other. So what would that floor look like? Like at any random floor, if you're going, what would that floor? What kind of load will that floor take, or what kind of load will a bridge take?
compressor?
Yes, but if you're putting a rod, like you'll be using rods to like strengthen.
Okay,
This.
so means it's like sort of like buckling type of thing.
Yeah. So
Like
essentially,
bending. Yeah.
you will have rods going through the roofs like this, right? You'll have these kind of rods which will be going through the roofs or through the bridges like this, right? So if you are giving like just a general rod, if you're putting it there, what will happen? After a point, it will start sagging, right? The rod will become something like this, right? Because of the loading.
Yes, sir.
So what engineers do in order to ensure that this does not happen, what they will do is they will put a pre-stressed rod, okay, stressing it in the opposite direction, stressing it upwards. So when the load comes, it becomes straight. understand that this will not be stressed so much that you can see that like a very clear arc. It will be stressed to a very little amount, but it will be stressed so that when the load is applied from the top, it becomes straight. So these are known as pre-stressed rods or pre-stressed materials. So in pre-stressed materials, your curve would start somewhere here. Okay, you'll have some negative value of epsilon naught, which will already be pre-present. And when the load is applied, it starts from there and then goes to 0. Okay, so essentially your strain becomes 0 at some value of stress. So this is a very good example, a very nice example that people have been using. Essentially, like civil engineers, more often than not, they use it for multiple applications because most of the structural buildings, etc., will have this kind of loading happening. So they will be using it more often than not. Civil engineers will be knowing this very clearly, this concept. Okay. So yeah. So there are few things that we have to take into consideration whenever we are talking about power law. Okay. So with that, we'll finish power law. So let's just write down the limitations of this entire thing that we learned about. Okay. So it is not very reliable for low strain. Okay. First thing, not very reliable for low strain values. That is strain values below 0.04. Okay. So it is not very reliable in that case. Next, it is not suitable to predict yield strength of the material. Okay. So this is, I think there was one example which was done in one of the NPTEL videos for this week. You can go back and refer to that video. So that clearly showed why this is not very suitable to predict the yield strength. You can remember it, but that is the example that you can use too. Okay. And finally, if the material is already work hardened, okay, the material is already work hardened, then you cannot use the general equation. We have to use a modified version of that equation. Okay. For instance, we used this sigma is equal to k times epsilon plus epsilon naught to the power n, right? So this equation, this case that we used earlier. So if it is already work hardened, then you have to use this kind of equation. Okay. So work hardened, the example I talked about, the pre-stressing, is also another kind of work hardening, which is a practical example of that. So if it has already been work hardened, you have to modify the equation accordingly. So these are the major limitations of power law, but still with these limitations also, this is one of the best equations to use for any application purposes that we have been looking at. So you can use this for measuring your flow stress and all the concepts around flow stress very easily. Okay. So now with flow stress concepts out of the way, let's move on to our second part of the discussion today, which is yield criterion. Okay, so we'll not be going very deep into all the concepts of yield. We'll be understanding it from the surface level. What are the criteria and why this criteria exists in the first place, etc. if you want to understand it much more deeply or understand the proofs behind why these yield criteria exist, there are multiple books which you can refer. Essentially, for the purpose of this course, we do not need the proofs. We just need to understand what these yield criteria are, why these yield criteria exist in the first place, and followed by how to solve problems if you're asked using a particular yield criteria. Okay. So, if you want to learn more about how a particular yield criteria was derived or how it has come about, then you can refer to some books, and those could be like your secondary reading. So, before we define yield criteria, like we already know, what is yield stress? What exactly is yield stress? Something that we can again remember or write down. What exactly is yield stress? Can anybody answer? Okay. So yield stress is the stress at which material will transition from elastic to plastic regime. Material transitions So essentially, when we talk about yielding criteria, what we are saying is the material will start deforming plastically after this point. Okay. So why it is important for us to understand yield criteria? Why are we talking about yield criteria in the first place? Something that we have already discussed previously. Can anybody recall? Why are we talking about yield criteria in the first place?
Sir, means like we in original cases we have three-dimensional stresses acting on a body. So
Okay.
in order to give it a set value above which the material will fail.
Okay, that's good. Uh, okay, means that I think you're talking about it from a perspective of how why we are talking about yield, like why we need to have a criteria in the first place. But why are we talking about yielding in the first place? Like, what is the reason behind it? Why do we need to understand yielding?
Sir, because we do not want plastic deformation during the service life of a material.
Exactly. So we do not want material to experience plastic deformation. In most of the structural applications, we want the material to be within its elastic regime. Why? Because if once the material hits the plastic regime, some permanent deformation will be present in the material, and that would cause some sort of failure or something else within the material. Okay, so you do not want any plastic deformation happening within the material. It is always safe to operate within the elastic regime. Now, essentially, then the second question comes: if it is so important to ensure that plastic region does not, like, we do not reach plastic region, we have to ensure that yielding does not happen, right? Now, if we are looking at uniaxial stress conditions, okay, if you're looking at uniaxial stress conditions, it is very easy for us to talk about deformations in that case, because you will have stresses acting along a particular direction, and you will say that, okay, if the stress does not exceed a particular value of stress, which is known as yield stress. So if the stress value that we are putting on the material, the load that we are putting on the material does not exceed the yield stress, then the material will not yield. Or if it exists, exceeds, or if it reaches that value, then the material will yield, right? However, when you're applying any other sort of stress which is not uniaxial, it becomes very difficult for us to figure out whether the material will yield or not. Essentially, because we do not know where the yield limit is, or which stress value we have to take in order to check whether the yielding is happening or not. So something that we can just a second. I think I had. So let me just write down this thing. Under uniaxial loading, it is very easy to equate state of stress to yield limit. Right? However, under biaxial or above kind of loading. So under biaxial or any other kind of loading, the yielding criteria becomes very difficult for us to ascertain. It's difficult to assert. Therefore, we need to create some sort of uh, concept in order. We need to have some sort of concept in order for us to understand what is yielding and what is yield limit. Okay. So there is something important that we have studied in the previous class known as Moore circle, right? So if we draw a Moore circle, let's say we are given a state of stress, something like let's take a 2D state of stress. Okay, say we are given something like 220, we are given something like 50. Okay, MPa, let's say in MPa. Unit does not matter right now, but yeah, and we draw its Moore circle. Okay, so 220 would be looking something like this. Let's say this is your 220, and then your 50 would be, say, somewhere here. Okay, so essentially what is happening here is your size of the Moore circle. Okay, the complete size of the Moore circle is determining whether yielding will take place or not. And it is not the actual value. of stress. Okay. Now it is very difficult for us to always draw Mohr circle and check whether like yielding is happening or not, right? So we have to define the whole thing in terms of, let me just add some pages. Yeah. So we have to define the whole thing in terms of some concept so that we can ensure that yielding is happening or not happening. We can find it in some particular way. Okay. Uh, so let me just write down. So to overcome such situations, we need to define yielding. In such a way that it should include overall stress state. Such a way that it includes the overall stress state. Okay, so essentially we have to write some function f for sigma x, sigma y, sigma z, tau xy, tau yz, tau zx to be equal to 0. Or not 0 exactly, let's say some c dash. Okay, some function which is equal to c dash. We have to equate it, and this c dash essentially is something related to the yield value, while this function is essentially giving us the overall stress state in some form. Okay. So similarly, we can write it in terms of principal stresses also, some other function. So it will be some other function sigma, which will take sigma 1, sigma 2, sigma 3, and it will be equal to some other constant c, which will again represent yield stress in some form. Okay. So now, before we move on to how to define the yield stress, uh, let's talk about what kind of material system we'll be dealing with while defining the yield stress. 1 second. Somebody was trying to join. Okay. Can you switch off your mic? Okay. Mute. I'm muted. Okay. So essentially, whenever we are defining these conditions, we will be defining it mainly for isotropic materials only. Okay. So all the concepts that we are defining here for yield criteria are for isotropic materials. There will be some change, some form of change that you will have to do when you're looking at any other material which is not isotropic. Okay. So when you're looking at cubic material, hexagonal material, or any other higher material which are having more elastic constants, you will have to tweak your entire uh, formula in some way so that you can accommodate those other elastic constants which are present. Okay. So some assumptions that you have to keep in mind: magnitude of your, sorry, did my screen switch off? Yeah, I think so. Just let me check. Okay. I hope my screen is visible now. Sorry about that. Okay. So yeah, we are talking about the assumptions. So I should, like for this case, so magnitude of the mean stress does not influence yielding. Okay. No Boschinger effect. Boschinger effect. What that means is your tension is equivalent to compression, right? I'll just write tension is equivalent to compression. Okay. Essentially, whatever route you are taking in tension, same route you will take in compression. That is what you are assuming. Okay. And you are assuming that volume remains constant. Constancy of volume. Now, in order to have a constant volume, you need to have mu or Poisson's ratio to be equal to 0.5. Okay. So first condition talks about the mean stress does not influence yielding. What could that mean? Why does mean stress not influence yielding? Why are we saying that? Okay, let's look at it from a mathematical point of view. So any stress tensor that we have, some sigma equal to sigma xx, sigma xy. So I'll just write it in terms of sigma xy xz like that instead of tau and all. So sorry. So any stress tensor which is defined like this, we can essentially break it down into two components. Okay. First is the hydrostatic or mean stress. Second one being your deviatoric stress. Okay. Now it is important for us to understand why we are breaking it down in such a way, right? What exactly is happening in a material when it goes through different zones, when it is in elastic region, when it is in plastic region, and when it is fracturing? What exactly is happening in material? Can someone summarize what exactly is happening at different places? Because we are dividing the entirety of the regions, the stress state or the stress strain curve, we are dividing into three parts, right? Elastic region, plastic region, and then fracture. Why are we dividing it in this way? What exactly is happening? Can someone tell? Okay, I will answer. So essentially, whenever you are looking at any material getting loaded, right? What is happening? Initially, the load will be acting on material in such a way that atoms are pulled apart to some small extent, right? When you're loading it within the elastic region, atoms are getting pulled apart by some value, right? And this region essentially defines the limit up to which atoms can be pulled apart before they can again come back together. So if you think about it in terms of energy landscape, if you remember, we had talked about this. previously. There is a attractive region, there is a repulsive region, right? And then like overall you will have a curve something like this, the energy versus something like this. Remember, energy versus distance curve. Something like this will be seen. So what essentially is happening is, till just a second. Am I audible?
Yes, sir.
Okay, I think just a second. There is some issue in my laptop. Got disconnected, I think. Sorry. Okay. Yeah. I think now it should be okay. Okay. I hope I am visible and audible. So yeah, like I was telling. So essentially, within the attractive region, within the elastic region, what is happening is this rule is being followed. Your energy versus distance rule. So till some point, right? Till some point, some cutoff, you will have the attractive part of the energy playing a role. So when you are pulling the material apart, your attractive part of the region is actually helping you bring the atoms back together to their equilibrium position. Okay, so if there are two atoms which is getting pulled apart, okay, to some value, once you leave that load, they will come back to their original case. This case that I have ticked, it will come back to their original state, to their main positions. So within elastic limit, this is what is happening. Okay. After elastic limit, what will happen? Now, if we look at atoms from the perspective of like two atoms just connected, or having some energy in between or some string in between or spring in between, which are like together, kept together, and then if you keep pulling them, what will happen? At some point, what will happen? If you keep pulling, like let's say you have two balls and you have connected them by a string, and you keep pulling them, what will happen at some point?
Fracture.
Yes, the string will snap, right? It will cause fracture. So if you're looking at it from the perspective of mean stress or hydrostatic stress, which only has pure tension and compression, okay, hydrostatic stress which only consists of pure tension and compression, you will not have anything after elastic, right? You will have elastic and then just fracture, right? But there is something else which also happens in essentially like in any material system, something that we actually account for, the plastic region. How we account for the plastic region? Something that helps us accounting for plastic region. If we are, so if let me just rub this part. So I hope you have understood where elastic region is ending and where fracture starts for pure tension or compression case. But in case we want to talk about something else happening, we need to look at some other kind of stress, right? So deviatory stress represents the shear stress. So I think from here you can understand. Essentially, so I don't want to go too deep into it because we'll be talking about dislocations in the upcoming class. But essentially what will happen is there are dislocations present within the structure. And these dislocations, what they are doing is they are influencing the material behavior. So when you're pulling, when you're applying tension also, even though atoms are like moving apart, it is not just atoms which are getting influenced because of the load. So you do not have all atoms placed perfectly next to each other. Like you do not have a perfectly ordered lattice. Okay. You do not have perfectly ordered lattice. Never in any real scenario you will have perfectly ordered lattice. You will have some sort of defects in between. Okay. And the most important defect that we usually talk about is dislocation. Now, because of this dislocation, I'll not tell you exactly what dislocation is and so on and so forth. But because of this dislocation, what will happen is your atoms are not ordered correctly. And if there is some gap or something, what will happen is now atom will jump from one position to the next position. Instead of it just staying in one position, it jumps from one position to the next position. Now, because of this jump, your material does not fail. Your material does not fail. Understand that. The material does not fail, but it starts flowing. Okay? Or it starts yielding. Essentially, this jump or this movement of atoms is controlled by shear stresses only. Okay, when we understand dislocations in much clearer sense, you will be able to understand why I'm talking about how this is only influenced by shear stresses. But this entire thing will be only influenced by shear stresses, and therefore this is the only thing that contributes to the plastic deformation case. I hope you have at least understood why your mean stress or hydrostatic stress is not contributing to the plastic deformation. At least that part you have understood. If you have not understood how your deviatory stress is contributing to plastic deformation, it is okay because we'll be understanding that mechanism in detail in the upcoming classes. So that part is fine, but at least I hope you understand why hydrostatic stress is not contributing to the plastic stresses. If not, just let me know. I will explain it again. Okay, I'll assume that you have understood. In any case, if you have, if you're still feeling doubtful and you have not understood, you just let me know. I'll explain it again, or we can take it up again in the next class also, where I'll explain it clearly as to how this is happening, with examples as to why shear stress is able to influence it. Okay, so this only involves only elastic changes in volume. Okay. So we want to ensure that this mean stress is completely taken out from this state of stress when we are talking about yielding. Okay. So what is this hydrostatic or mean stress? Sigma h or sigma m, whatever, however you want to write it. Okay. This is equal to sigma x plus sigma y plus sigma z divided by 3. Okay. Essentially your this plus this plus this, the three things I have underlined, divided by 3 will give you your mean stress or hydrostatic stress. Okay. So this in terms of principal stresses, like we had talked about some invariants, right? I1, right? I1 is sigma x plus sigma y plus sigma z, right? So I1 by 3 will also be giving you the same value. Then how do we get deviatoric value of stress? Sigma d, that is equal to sigma minus sigma h. Okay. Or you can write sigma m. Let's write sigma m mean. Okay. So essentially you will have sigma xx minus sigma m tau xy, tau xz, then tau xy, tau xz, sigma yy minus sigma m, tau yz, sigma zz minus sigma. Yeah, let's use small m to represent mean stress here also. Okay. So here, what can we say about deviatoric stress? Something important that we can say about the deviatoric stress. Hydrostatic stress is only including components. Let me just keep chat open. Yeah. Hydrostatic stress is only including components from the diagonals, right? However, your deviatoric stress is including components from all the places, right? Not just the diagonals, also non-diagonal elements, diagonal elements. It is including all the elements together, right? And another important thing that you can see here. If you look at the invariants, one important thing that you can note for deviatoric stress, or more specifically, if I want to say, your I1 for sigma deviatoric is equal to what? It's not. Your I1 for sigma deviatoric is equal to what? Okay, just write it down. Sigma x minus sigma x plus sigma y plus sigma z by 3, right? So that will be equal to 2 sigma x plus sigma y, sorry, minus sigma y minus sigma z by 3, right? Plus your the y component will be 2 sigma yy minus sigma x minus sigma z by 3, plus your zz component will be 2 sigma zz minus sigma x minus sigma y by 2. So summation of all of this will lead to your I1 will be equal to 0. So your deviatoric stress, your invariant 1 is equal to 0. Okay, or your mean stress is equal to 0. That is something that you can remember. So finally, what you have to remember, your mean stress is composed of only hydrostatic or the pure tension and compressive stresses. Your deviatoric part of the stress is only composed of shear. Okay, it is not composed of any value of whether it is tensile or compressive. Any normal stresses it is not taking into account. Only it is taking into account the shear values. Okay. Now let's talk about your yield criteria. Now that we have understood these concepts, let's go into the yield criteria. So there are some requirements that you need to satisfy for yield criteria. So since your deformation is majorly occurring by shear only, it should be only a function of deviatoric stress. right? Something that you can keep in mind. It should only be a function of deviatoric stress. Next, the vice versa of that. Actually, let me just write it together then. Should not be a function of hydrostatic stress. Okay. Another important thing that you have to keep in mind that it should not depend on the choice of axis. So yield criteria should be axis independent. Okay, it should be independent of the axis that we are looking at, and it should not be the final thing that we have, which we saw already in case of Mohr circle, right? We already defined it here. That size of the Mohr circle will determine your yielding criteria and not the position. Okay, it's not the position or the value of individual stresses. It is size of the Mohr circle which will determine your yielding. Okay. Yeah. One more page. I think that should be sufficient. Okay. So now let's move on to some well-known yielding criteria which is used almost everywhere. Okay. The first one is of course von Mises, which is the most used yield criterion. So your J2 plasticity, second invariant of the deviatoric stress. Second invariant of deviatoric stress is a good candidate for determining your yield criteria. So this is what essentially von Mises criteria states. Okay, so this is your essentially your von Mises criteria. Second invariant is a good candidate for determining the deviatoric, for determining the yield criteria. Second invariant of the deviatoric stress. So essentially your J2, okay, your is basically I2 only, but we call it J2 so that like we can say that it's deviatoric stress component, not the entire state of stress. So if you're talking about the entire state of stress, we will use the term I1, I2, I3. But whenever you are using only deviatoric stress, we will say J1, J2, J3. Okay, it's one and the same thing only. Just to keep a distinction between total state of stress and deviatory state of stress. Okay. So if you're writing it in terms of principal stresses, okay, plus this is your J2. So essentially, if we take this function in terms of functional form, okay, so we'll remove the constant, the 2 by 9. Okay, so it's just is equal to some constant c. Okay, now this c is basically the critical value. Okay, c is the critical value. Critical value that the material needs to exceed for yielding to happen. Okay, so this is the critical value that determines yielding. Okay, so essentially for von Mises case, we can write this function and the final expression essentially in this form. So your sigma x minus sigma y square plus sigma y minus sigma z whole square plus sigma x minus sigma z square plus 6 times tau xy square plus tau yz square plus tau xz square is equal to 2y square, which is equal to 6 times some k square. Okay. Now this is a generalized form of von Mises criteria. Okay. So what we are writing is C is equal to 2y square. Okay. Y is the yield stress. Yield limit or yield stress. Okay. So this criteria, I mean, you can write it in terms of principal stresses also. Sigma 1, same thing, what I wrote on top. Sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 whole square is equal to 2y square. So same, exact same relation. Okay. So this is your von Mises criteria. One more important criteria, we'll discuss that, then I will draw and show how these criteria look on any in a stress graph. Okay, in a stress graph, how these look in a 2D state of stress. So your Tresca criteria. Now this is far more simpler compared to von Mises. Okay, this is also known as maximum shear stress criteria. Okay. So essentially, what this criteria states is that shear stress is the one that causes plastic deformation, right? Like as we have seen till now, shear stress causes plastic deformation. Okay, and yielding will occur when the largest shear stress reaches a critical value. Okay, so essentially, instead of taking into account hydrostatic stress, deviatoric stress, etc., it just skips over all that. It just takes directly whatever is the stress value, the largest stress value, largest shear stress value, and then just equates that to the critical stress value. Okay, so if we have principal stresses sigma 1 greater than sigma 2 greater than sigma 3, like if you have arranged them in descending order, then your largest value of shear stress is given by sigma 1 minus sigma 3. So that is equal to your critical value. Okay, or y, your yield limit. So in terms of k, you can write it as 2k. So this is essentially your Tresca criteria. Now, if you look at the region that these two criteria are encompassing for biaxial state of stress, you'll see that there's some yield point, some yield point. Okay, yield point is same because we are talking about isotropic case. This similarly here also. Okay, so what your Tresca criteria does is it encompasses this region. Okay, so this is your uh, Tresca region. Okay, the yield region for Tresca. While von Mises will encompass something like this. Okay, I'll draw it in different pen. Okay, so essentially you have this extra part, the green shaded region, which von Mises also takes into account while looking at yielding, while Tresca is encompassing a much smaller region. Okay, so if I'm talking saying that, say this is sigma A and sigma V, the back biaxial stresses, and these are all yield. This is y, this is also y, this is also y. Negative, let's say this is negative. So your von Mises stress is encompassing a much larger area compared to Tresca. Okay. So it is important to note that your Tresca is a little more conservative, while von Mises is giving you a much more truer picture, much more closer to reality picture. So therefore, von Mises is the one which is generally used in most of the cases. But Tresca also gives you almost similar values only. Just in some cases, the border cases, you will see that the values start diverging. Okay. So yeah, uh, this is about the two criteria for yielding. Okay. So there is another failure criteria. Okay. Now I call this a failure criteria, not a yielding criteria, because this does not talk about yielding. Rather, it talks about failure. Okay. So this is known as Rankine or maximum principal stress. Okay. Now, what this states that yielding will occur when maximum principal stress at any point reaches the yield limit of the material. So essentially, your maximum principal stress becomes equal to y. Okay. But understand that this is defined for failure, not for yielding. Okay. Because you are taking into account only the hydrostatic state of stresses. Therefore, there is no. I'll write it down. It's okay. So essentially, this is defined for failure and not yielding. Okay. So what that means is that you are only looking at hydrostatic state of stresses. Okay, essentially, and then you do not have any plastic region. You're not playing around with the plastic region. So you are completely ignoring all the shear stresses, etc., which can influence the plasticity. So therefore, you will have elastic region and direct failure after that. Okay. So only hydrostatic state of stresses you are looking at. One last concept that we will talk about before we move on to the problems for today. Concept of effective stress and effective strain. Now, very important in case we are looking at failure criteria or yielding criteria, because we need to understand what is the effective value of stress for a particular state of stress, and that we can equate it directly to the yielding value, so that we can get the value of failure directly. Okay, so if you can remember this, we can directly apply it. So for instance, in von Mises, if I derive the entire thing, I will not go through that, but like my my effective stress, okay, is equal to half of sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square whole root equal to your yield limit. Okay. So this is your effective stress for von Mises. So I'll just write it as V. Okay, sigma. For your Tresca condition, extra criteria, your effective stress is equal to sigma 1 minus sigma 3. Provided sigma 1 is the largest, the maximum value of principal stress, sigma 3 is the minimum value of principal stress. Okay. That is equal to 1. So similarly, we can find effective strain values also. However, one important thing we have to keep in mind while talking about effective strain, although effective stress is written from the perspective of yielding, effective strain is not written from that perspective, that yielding will happen if it exceeds this strain value or etc. etc. No, that is not the way in which we are looking at strain. What we are looking at is incremental work done okay, per unit volume it's constant. Is not constant, consistent. Essentially, what we're trying to say is the incremental work done due to this stress and strain. So you will know that work done is equal to stress times strain, right? So incremental work done due to this stress and strain is consistent per unit volume. Okay. So based on this criteria for von Mises, your effective strain value would be root 2 by 3 times epsilon 1 square plus epsilon 2 square plus epsilon 3 square. Okay. While for Tresca it will be your epsilon I, okay, maximum. So maximum value of maximum principal stress value, whichever is the maximum principal stress value, you just take that, and that will be your the magnitude of that, not the sign. So you take the norm of all the three principal stress values, and whichever is the maximum one, you just take that. Okay, the mod of a norm of that. So with that, we will come to the end of the theory part of today's discussion. We'll move on to the problems for today. But before that, let me just give me just a second before I move on to the problems. Just 1 second. Okay. So let's come back to the problems for today. So our first question is, they have given us 2 points on a flow stress curve as 0.05, 200 MPa and 0.15, 300 MPa. They are saying that assuming power law behavior for the material, find the true stress in MPa at a true strain of 0.3. Okay. So very straightforward question, right? They have given us 2 points. So using that, we can find both the K and N values for the power law. And once we know that, we can substitute it to find the new stress value. Okay, so let's try and solve this. So 2 points that we have are 0.05, 200. The other one is 0.15, 300. So these are the 2 points that we have. So your power law is given by K F sigma is equal to K times epsilon to the power N. Right. Now, if I take natural logarithm on both the sides, okay, I can write ln of sigma is equal to N times ln of epsilon plus ln of K, right? So if I substitute it for sigma 2 and sigma 1, what will I get? I will get N is equal to ln of sigma 2 divided by sigma 1, right? Divided by ln of epsilon 2 divided by epsilon 1. Because your ln of K by K, like ln of K, will just cancel each other. Both the ln of K will cancel each other. So if I substitute the values, I will get ln of 300 divided by 200 divided by ln of 0.15 divided by 0.05 or ln of 3 by 2 divided by ln of 3. So let me just calculate it. So the final answer is 0.36. So n is 0.36. Right? Now, if we substitute for one of the cases, let's say 200, 0.05, 200, 200 is equal to K times 0.05 to the power 0.36 is equal to K is equal to, let me just calculate. So this is equal to 588.03 MPa. Okay. So finally, they have asked us for 0.3. At 0.3, what is the? Just a second. Yeah. So they have asked us at 0.3. What is the value of stress? Sorry. Yeah. True strain 0.03. No, 0.3 only, not 0.03. 0.3 only. So they have asked us sigma value at 0.3. So this is equal to 588.03 into 0.3 to the power 0.36. This is our final answer. So let me just calculate. So final answer is 381.2 MPa. Okay, so if we see the options, second option is the right one. Okay, I think this has moved. Let me just move it. Yeah. So let's move on to the second question. They have told a material is deformed under tensile condition up to 20% elongation. Okay. Assuming that the material shows power law behavior, find the final flow stress of the material in megapascals. Value of K and N are 220 megapascals and 0.3 respectively. Okay. So they have told that a material is deformed under tensile condition up to 20% elongation. So your sigma E, sorry, epsilon E, your epsilon E value, strain value, engineering strain value actually, is equal to 0.2. So your true strain value will be equal to ln of 1 plus E, epsilon E, okay. So this is equal to ln of 1.2, which is equal to 0.18. So 4 decimals, 0.1823. Okay. So this is your epsilon. Now they have to ask us what is the value of stress, final value of flow stress. So sigma is equal to K times epsilon to the power n, right? So this is equal to 220 into 0.1823 to the power n, which is 0.3, right? So your final answer is, let me just calculate it. So final answer is 132.025 MPa. Okay, so this question is done. Next question, they are telling a material is deformed under tensile condition up to 20% elongation. Assuming that the material shows power law behavior, find the average flow stress required for deformation. So it is the same question what they have asked us previously, but this time they are asking us to find the average value of flow stress for deformation. Okay. So how do we find average flow stress? So essentially, what is the thing that we are trying to find? We are trying to find stress value, but averaged over a region, right? So how can we do it? If we take the area under the stress curve, we will get work done, right? But that work done varies with respect to the strain. So if we take total strain and we take the total area and divide that by the total strain, the total area under the curve, the work done, divide that by the total strain, we'll get the average value of stress, right? So if we take 1 by epsilon times varying 0 to epsilon, your sigma times d epsilon, we will get your average value of flow stress, right? So sigma d epsilon will give us k times epsilon to the power n plus 1, right? Divided by n plus 1. And already we had one epsilon in the denominator. So it becomes K times epsilon divided by n plus 1, or sigma divided by n plus 1. That's your average value. Okay, let me write the intermediate step so that there's no confusion. So this will become K times epsilon to the power n divided by n plus 1. So K times epsilon to the power n is equal to sigma divided by n plus 1. Okay, so average flow stress is equal to whatever is the flow stress value that we got previously divided by n plus 1. So your average flow stress (132.03), right? 132.03. Previous question divided by n plus 1. So n is 0.3 plus 1. So this is equal to, let us calculate, so final answer is 101.55. And the 1.55 closest value is this one. Third option is the correct option. Okay. So moving on to the next question. So next three questions are theory type questions. So we can just discuss them directly. They have asked us which of the following assumptions are made for isotropic materials for a valid yield criteria. Okay, so we had discussed these assumptions, right? So first one, they have asked Poisson's ratio. They have said Poisson's ratio must be 0.5. So that is correct, right? We want volume to be constant, so Poisson's ratio should be 0.5. They have told us no Boschinger effect is observed during deformation, which is also correct. We do not want any Boschinger effect. Compression and tension should be equal. So that is also correct. Next option, magnitude of mean normal stress does not contribute to yielding. Again, that is correct. And finally, volume may not be conserved. No, we want the volume to be conserved, so that is not a correct option. Okay. Next question, which of the following statements are true for the stress tensor with respect to deformation? So, first option, hydrostatic stress is only responsible for elastic volume changes. That is true, right? So you can take that. Next option, deviatoric stress is responsible for plastic deformation. Again, that is true. We discussed that today. Next option, deviatoric stress involves pure tension and compression. That is false. It only involves shear part, not the tension and compression part. And then hydrostatic stress represents shear, which is again false. Next question, which of the following are necessary conditions for a valid yield criteria? So first one is it should be independent on choice of coordinate axis. That is correct. It should be some function of shear stress. Again correct. Yielding is only dependent on shear, not on tensile and compressive part. Then mean stress should not influence yield stress. Again correct. We do not want any mean stress or tensile or normal stresses influencing the yield stress. And then it should be a function of hydrostatic stress. No, that is wrong. That is exactly opposite of what we read in the previous option. So that is wrong. Okay. So yeah, so these are the three theory-based questions. Next, again, we'll come back to another problem. They have told us a circle of 0.22 meter in diameter was printed on a thin sheet of metal prior to stamping operation. After stamping, the circle changed into an ellipse with major and minor axis 0.3 meters and 0.26 meters respectively. Okay, so in both the direction it has expanded. Assuming proportionality of strain during deformation, determine the effective strain in the region of ellipse. Okay, so we are assuming proportionality of strain, and we have to determine the effective strain in the region of ellipse. So strain we have to find, not stress. Okay. So since they have asked us effective strain without mentioning which kind of effective strain we should find, we'll find von Mises strain. Okay, we'll not find Tresca. We'll find von Mises. So what essentially they are telling in the question is, initially there is a circle. Okay. So your radius is 0.2 meter, and then it changes into an ellipse. Sorry. Not exactly looking like an ellipse, but I hope you can assume that it is an ellipse. So it is 0.3 meters on this axis and 0.26 meters on this axis. Okay. So it changes into an ellipse from initial to final. So your stress in the, let's say your this is your direction 1, this is your direction 2. Okay, so epsilon 1 is equal to ln of 0.3 divided by 0.2. Okay, so and your epsilon 2 is equal to ln of 0.3 divided by 0.26 divided by 0.2. So let's calculate both the values. So answers are 0.31 and 0.167. Okay, that's your epsilon 1 and epsilon 2. Now your epsilon 3, because it's we are assuming a constancy of volume, should be equal to negative of epsilon 1 plus epsilon 2, right? Because it's constancy of volume, your changes in strain in the other two directions should be equal to negative of the change in strain in the final direction, right? So if we add them, we just add them. Negative of 0.477, straightforward. Okay, so finally our effective strain epsilon is equal to root of 2 by 3 epsilon 1 square plus epsilon 2 square plus epsilon 3 square, right? So let me just substitute and write the final answer directly. You don't have to do the whole calculation. So final answer is 0.48. Let's see if there is a point. Yeah, this is the answer. So we have got the final answer correctly. Next question. They are telling us to find the effective stress state. They are giving us a stress state for aluminium component, and they are asking us to find the effective stress using von Mises criteria. Okay. Again, all the stress values are given to us. So effective stress is equal to 1 by root 2 times sigma x minus sigma y square plus sigma y minus sigma z square plus sigma x minus sigma z square plus 6 of tau xy square plus tau yz square plus tau xz square whole to the power 1 by 2. So this is our expression. What and all do we have? 1 by root 2 sigma x minus sigma y. We have sigma x, sigma y, sigma z. All three we have. So we can just write 120 minus 240 square plus 240 plus 120. 240 minus of minus 120 will be plus 120 square plus 120 minus of minus 120, so 120 plus 120 square plus 6 into, so only xy is there. There is no yz and xz component, so xy 6 into 80 square whole to the power 1 by 2. So let's calculate and write the final answer. Final answer is 346.4. Let's see if any option matches that. 346 is given, so that should be the answer. Okay. So we have time. Okay, we're almost running out of time. But let's just do this one question and then we will end it. Okay. A component is in plane stress state and known that yielding begins in a material at following stress state. Sigma x is equal to 150 MPa, sigma y is equal to 200 MPa, and sigma xy is equal to 30 MPa. Considering Tresca criteria for yielding, what would be the yield strength of the material? Okay, so they have told us yielding would begin at the following particular stress rate that they have given us. Okay, what is the stress rate they have given us? Sigma x is equal to 150 MPa, sigma y is equal to 200 MPa, and tau xy is equal to 30 MPa. Right, and they say that sigma 1 to 2. Okay, so they are telling us to find it using Tresca criteria. So we'll use Tresca criteria to find all the three principal stresses. Now, since it is a biaxial state of stress, your principal stress in the third direction will be equal to 0 because there is no sigma z or any component of stress acting in the z direction. So let's find sigma 1 and sigma 2, and sigma 3 will be anyways equal to 0. So there is a direct formula, right? We already know this. Sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y, right, whole square divided by 2 plus tau square, right? This is giving us both sigma 1 and 2. So let me calculate and write the final answer directly for both the cases. So one value I got was 214.05 MPa. So the other one will be negative of something. So negative of that. So let me just put negative sign and recalculate. This is 135.94 MPa. So we want to take the largest value. Of course, sigma 3 is equal to 0. So largest and smaller value will be 214.05 and 0. So according to the Tresca criteria, we will have y is equal to sigma 1 minus sigma 3. So that is equal to 214.05. Right? So the closest value that we get is this one. Right? So with this we'll come to an end for today's discussion. I hope you have understood all the concepts related to flow stress and yield criteria and understood how we have solved the problems for these concepts. In any case, if there are any doubts, we can talk about them in the next class. We can discuss them in the next class. So with that, we will end today's lecture. Thank you for attending and thank you for listening.